Hey folks, the following interview is the first of our two-part keynote with Deborah Mayo. Although this is the first time that I will have spoken to her in person, I've always enjoyed reading Deborah's thoughts on various statistical controversies and how they can apply to us better understanding and having a more rigorous approach to science. I've also always enjoyed how she does not steer away from challenging or controversial statistical issues, especially when they are very important to the community. The first part of Deborah's keynote will be this interview here, followed by a presentation by Deborah. I think that's the most time-efficient way to get through the ideas that we want to cover, many of which are also covered in her recently published book, Statistical Inference as Severe Testing. I think that severe testing is a very interesting idea, and one that data scientists should consider entertaining as a way to help them more rigorously assess the claims that they are making from their own data and data analysis. Deborah's work has been celebrated by the philosophy of science community, not limited to her winning the Longitude Award, and I think you'll enjoy her too. Enjoy the interview. Hey folks, welcome back to the Philosophy of Data Science series. Today we have something really special. It's our first keynote conversation. It's with Deborah Mayo of Virginia Tech, and it's pretty exciting because we are finally having a philosopher of statistics discuss and introduce us to the field and some of the controversies, challenges, and interesting thoughts around it. And I really enjoy reading Deborah's work. This is the first time I've actually spoken to her in person, but reading her work is really interesting and very thought-provoking. So right now I am armed with a large number of notes, and we will go through this journey together to better understand some of the issues surrounding the application of the philosophy of science in statistics. So welcome, Deborah. Thanks so much for coming in. And maybe we should start by if you just introduce yourself, your research interests, and et cetera.
Thank you so much for inviting me. I'm very, very pleased to be here. My general area of research is in philosophy of science, and specifically in philosophy of experiment, inductive statistical inference, and interdisciplinary work relating values and science. So my recent book is Statistical Inference as Severe Testing, How to Get Beyond the Statistics Wars. Prior to that, I have Error and the Growth of Experimental Knowledge, and these kind of all interrelate the different ways in which statistics, induction, and general quantitative methods interrelate with philosophy.
Great. And just as a quick follow-up on your books, there's the Lactose Award. Could you please describe that in a sentence or two? Both of our keynote speakers so far are winners of the Lactose Award, and he's been mentioned in our previous conversation with Andrew Gelman, but could you just explain what that is, why it associates with you?
Yeah, the Longitude Prize is a prize to the best, what's considered by a group to be the best work in philosophy of science over the past 60 years. And it's not considered a lifetime award. It's supposed to be given to somebody who's sort of mid-career. And it needn't have anything to do with the philosopher Longitude, although I thought that my Error and the Growth of Experimental Knowledge clearly was an extension and maybe an improvement on Longitude. So I've been involved in the London School of Economics, and that's one of the reasons, because the prize comes out of that field. And our field doesn't have many prizes. Since then, they have developed a couple of additional ones, but at the time, it really was the only one, the main one.
Great. And we have quite a few things to unpack today. We won't necessarily cover them in this order because we're just have a normal conversation. But basically, we have quite a few things. We're going to talk about the philosophy of statistics. We'd like to talk about some severe testing and how that applies to issues around, scientific discovery, scientific process, and also generally what are many of the statistics wars, just to use your term, and many of the controversies. Actually, they revolve around these philosophical underpinnings, whether or not we recognize them. So there's quite a few things to unpack. But we'll just get started and see where the conversation takes us. Cool. So just to begin, maybe we should just start with the philosophy of statistics and just sort of, there's two questions here. What is, I guess maybe three if you want to say, what is statistics? What is the philosophy of statistics? And then a separate question of, does philosophy apply to statistics? And we can start that conversation in any order.
Okay. I might say generally, I might actually start with generally, philosophy of science looks at the foundations of the methods for learning from data. And in a sense, philosophy of science asks a lot of the same questions as statistics. What's a reliable observation? How can we make inferences and predictions that work? What counts as a good test? When do we have confirmation? So they're similar questions. So it's not surprising that statistics really veers into philosophy very often. Now, statistics, I suppose, could be understood as using data to learn about the processes that produce that data and to add to any inferences that you make some sort of qualification of the uncertainty involved. So I said philosophers of science and statisticians in one sense ask similar questions. In fact, Oscar Kempthorne said philosophy of science was applied statistics, applied philosophy of statistics. But the way philosophers answer those questions is quite different. There's a certain level of generality in philosophy that you're not going to find in statistics, which deals with specific problems. So we might talk in general about what counts as a good test, what counts as reliable evidence, does simplicity matter, and so on. Much more general. By and large, philosophers have utilized statistics in grappling with their own problems, in setting out what philosophy of science might be doing in characterizing science. Okay, so we're actually looking to statistics to get some ideas about the nature of inductive inference and the role of probability in inference. In the other direction, philosophers whose job is really to clarify conceptual confusions of scientists are also interested in resolving the problems faced by statistical practitioners. Still, I admit that you, as a practitioner, wouldn't directly get answers to your problems opening up a philosophy of science text. I have tried in my last book, and certainly this one, to bridge the gap between what philosophers of science do and real live statistical controversies.
Yeah, and just to sort of follow up on that point, tangentially, one of the things that I found most helpful in, for example, my own work in machine learning and healthcare is the framework that the philosophy of science gave, and just our more general reasoning, where when you start discerning between whether or not you're making a form of deductive inference versus inductive versus abductive, for these fields like machine learning and AI, the problem, one of the main problems comes with that. We're essentially dealing with a so like a tangled knot of all these issues together. And if we don't actually understand which logical framework we're using at each step, then it becomes harder and harder to debug things if they don't work as we expect. So it's important to know if you're making an inferential leap or an inductive leap versus a deductive step, so to say. And so that's one of the reasons why I actually first came around to your work, some of Andrew Gelman's work on specifically the philosophy of science, and also Samir Akash's work on this, just describing these issues in general, just to try to get my head wrapped around how I should be viewing some of these questions myself. But I was curious if we could go back to what you said about how philosophers use statistics to help them understand what's going on, because one thing that seems strange to me is I always thought it was like philosophers as well. It's like they're going to be the ones, they'll just deduce it from principles and things like that. But obviously that's not quite right. So could you give us an example of how
philosophy deduces things from first principles? Well, we are very interested in understanding science, what makes it work. And naturally, the actual methods of science are going to be relevant. It's true that in the logical positivist era, there was much more of an analytic job where philosophers would see their task as defining terms. So an agent X knows that P, if and only if P, proposition P, is true and it's been attained by a reliable method. And they would not go into the details of what counts as a reliable method, which would require looking at some methods from probability theory or statistics. I guess starting around the 1960s and 70s, philosophy of science became more naturalized, as we say, and we committed ourselves to being relevant to science, but also to making use of methodologies from scientific practice in general, and statistical practice would be a particular example. But there's something you had said before in delineating induction, deduction, and so on. These terms are very complicated. I would say that the one thing that a practitioner should take away from thinking about philosophy is that these are not cut and dried terms or ideas, and they should be very reluctant to accept without critical scrutiny what somebody says counts as induction, deduction, abduction, which is another term bandied about quite a lot these days. So I tried to build from scratch in my work to offer answers to these questions, and they're not going to be the same as what somebody else does. So that's the most important thing you might say to learn from philosophy. These are not settled matters. The situation is radically different from what you face in other professions where you could look things up. Although there are debates about statistical terms also these days, but here they're very deep differences, and what I think practitioners can take away from philosophers is how to become better applied philosophers of science so that they can critically assess if they're doing deduction, induction, abduction, if what counts as reliable, what's the role of probability, and the nature of statistical inference, that they can cut through some of the memes that are bandied about all the time, like all models are false. Everything is equally subjective and objective. Well, we know from the gurus who tell us, you really need to critically evaluate those. And that's what I think philosophy most can offer.
Yeah, and yeah, because I guess one of the questions that I wanted to answer, which you have just answered in turn, is say, imagine there's the petulant question. What do philosophers who might not be, who almost certainly aren't, analyzing data on a day-to-day basis, what can they tell me about analyzing data on a day-to-day basis? And I think that it is important to understand that this is the idea that we examine these tools, we better try to better understand them so that we can apply them ourselves. It's not like there's going to be some top-down lesson from on high that will essentially give us the answer to all of our difficult questions.
This kind of critical capacity is not something that you typically see. I say in my book, it requires a lot of chutzpah, where you're prepared to take on the high priests in your field and question when they tell you about what is a warranted inference, and also what they tell you about the history of statistics and the field. But I'm prepared to say that by and large, science goes on without looking to philosophy to succeed. I think there are only certain special times in a particular scientific practice where philosophy is altogether important. In the case of statistics, I think it enters when you're interested in developing new methods or in trying to justify or critically appraise the warrant of methods, or when there's kind of a crisis about the very fundamental goals and methods in the field. And I actually think that statistics and also data science are in that kind of a situation now. As Tom Kuhn said, it's only in times of crisis that practitioners behave as philosophers. And I do think this is one of those times. I'm sure that we'll elaborate on that as we go.
Yeah, actually, why don't you elaborate a bit on that now? Because obviously, there's going to be a session later where we talk about Popper and Kuhn and some of these issues of scientific revolution. And so, when you say that science does by and large just sort of truck along on its own, not thinking much about philosophy, and that's generally called, I guess, the term like normal science comes into play, where people are incrementally building upon a current framework of learning, and then there are times where it simply becomes untenable to be holding to that, and you need to make a sort of a change in another direction, or just a large overhaul of the general like framework by which you're examining these phenomena. And that's when people start going into philosophy to start having a better idea how to critique what previously was happening. Is that sort of the...
Yeah, well, I think that gets at the gist. It's true that statistics has actually always been mired in philosophical controversy. The role of probability and inference has been a big question. Should probability enter to ensure that we don't make erroneous inferences too often in the long run, or should probability enter in order to quantify our degrees of belief or support or comparative levels of support? The basic fundamental goals, they've always been disputed. But I think today the reason it's even more pertinent are two main things. One is the so-called statistical crisis of replication, the fact that effects that had been found to be statistically significant are then not found significant when an independent group seeks to replicate them. And then there's also the introduction of data science not so many years ago, which really sent statisticians' wheels spinning as to whether they were not really data science and why were these other people coming in and sort of taking over. And those two things, I think, and of course what goes along with data science is the fact that we have these high-powered computerized methods which might give us lots and lots of data. And the question is, it becomes so easy to find impressive looking effects, even though they're actually spurious. All of these recent things makes it even more pertinent to go back and look at the arguments and the specific reforms that have come out of trying to grapple with the replication crisis are things that desperately call for philosophical scrutiny, and they have not been given that. And I think it's very urgent that people do so, because methods are being shunted aside, maybe banned even, without a really reasoned, philosophically based scrutiny of the arguments. So we recently at the joint statistical meetings had a session that was called Significance Test, Deconstructing the Arguments. So that was the point. Is that sufficient? You get the idea of, the forces that I think make it even more philosophical than the typical situation.
Yeah. And I guess even people outside of statistics now are, I think when this replication issue is coming about, that people are essentially, even if they aren't practitioners of statistics, are essentially laying this replication crisis back at the feet of statistics, saying, well, didn't you tell us, X, Y, and Z would happen if we applied these methods? And now statistical methods essentially have to answer, well, either that isn't what we were saying, or this is misunderstood. So, I think that this does bring about why we have to be examining on a greater level the exact implications and the underlying assumptions of what we're doing. Can you put that in a more eloquent way?
I think that many of the reforms in order to improve on replication are good. For example, you shouldn't be using statistical tests in an unthinking cookbook manner that has long been derided. They should be thoughtfully used and blended with empirical and theoretical background ideas. Then there's also the idea that we ought to pre-register our results, our hypothesis, so that somebody can critically evaluate the probability that you would have found something that looks impressive, even if it's due to chance. So there have been some good reforms, but others are quite radical, and I say even can obstruct practices known to improve on replication. And that's why it's so important to understand the philosophical basis for some of these arguments. I can give you an example. The American Statistical Association put out this statement on p-values in 2016, which really did just rehearse a lot of the claims about what a p-value is and how to avoid p-values. Not a posterior statistical significance, is not substantive significance. No evidence against a claim is not evidence for it. Well-known claims. But then a few years later, in 2019, some of the same authors put out an editorial which was sort of presented as if it was just a continuation of the 2016 statement, but it was quite radical. It actually said it's time to stop saying statistical significance altogether, and it's time to not use statistical thresholds in interpreting data at all. And I actually think that these suggestions, although I understand where they may be coming from, defeat some of the most important things. Because if you don't have a threshold, okay, then you really don't have a test. It's necessary that at least some of the outcomes won't be allowed to count as evidence in favor of a claim in order to have a test. And that's tantamount to having a threshold. I mean, so this is this big debate, and I don't know whether you want to get further into it or not, but basically, I think some of the reforms that are thought to be good things, after all, you might say, if you don't have to meet 0.05 or 0.001 or whatever threshold is, then maybe you're not going to be lured by these so-called perverse incentives to try to cherry pick and data dredge. And that's, of course, the key problem behind non-replication. But in fact, a researcher is still going to want to show that they have evidence of a real effect. They're still going to have to, in effect, show a small p-value. To take a non-statistically significant p-value and claim this is good evidence for an effect would actually not make sense. It would be to say that even though the probability of larger and more extreme differences than I got often occurs by chance alone, I claim this data are good evidence for non-chance. So what happens is that the researcher, still wanting to show an impressive effect, would be led to data dredge, to change the endpoint, and so on. The only trouble is, without the thresholds in place, it would be very hard to hold them accountable. So I say that it would actually obstruct practices known to improve on replication instead of helping things.
Yeah, I'd like to go into this a little bit further, but first I wanted to do some quick sweeping work because we introduced some ideas and then moved away from them. But very quickly, the issue of hypothesis pre-specification. As you know, there are quite a few fields that do, even from a regulatory sense, require that. Do you think that the areas in statistics where people are still working on pre-registering their hypotheses, for example, are those having less of the replication crisis problem? So by following better standards, are they having fewer of these problems than, say, the average nutritional study?
Although I don't have numbers, I think it was found right away that, in fact, there were a lot more negative results when you pre-registered. So you might have previously gone ahead and published it as a genuine effect. And so it is known to be a very important way to improve on replication, even though there are difficulties in sustaining it and in showing that you really have stuck with the pre-designated plan, sampling plan.
Yeah, because when the issue of pre-registration comes up, obviously, with my own like healthcare perspective, usually the first thing that pops in mind is like clinicaltrials.gov. There are some places where they have an industry standard towards these, and there's also a lot of hand wringing about not only how you pre-specify your primary hypotheses, but how you specify the order in which you care about them and things like that. And so you can then compare that to actually now I'm in a little bit of a pickle. Part of me wants to talk a little bit more about the replication crisis, and the other bit I'll make a note, and we'll come back to one of these other questions later. But yeah, where would you like to go from there? So part of me wants to go.
Okay, I think I have the possible good way to blend. And if you think about what goes wrong there in the case of lack of replication, I think you're led to this basic principle that I think is the one to begin with in evaluating statistical methods. Because if you're allowed to data dredge and try again, the thing is you can ensure that you will find something that might be impressive looking just by chance alone. And the trouble there is that you really haven't done anything to critically probe that, in fact, this is merely due to chance. And as a result, you kind of violate what I consider to be, what most people consider to be the most minimal requirement for evidence, that in order to have evidence for a claim, something has to have been done that could have found the claim false or flawed in some specific way. So I call that the minimal principle for evidence, the minimal principle for a severe test. So maybe that is the connection between the replication and this idea of a severity principle.
Yeah, that's where I wanted to go next. I think that's probably the most important thing to cover so far is if we could start talking about the severe testing framework, what the idea is, what the criteria are for strong versus weak severity in testing or weak testing. Because I think that this is one of the things where when you take this and apply it to your own field and ask these questions, has this claim that in a publication been severely tested? Once you put it in the wording that I think that you use, a lot of the answers tend to be no. And so I thought that, yeah, let's get the show on the road on the severe testing, because I think that's really important.
Well, I think this is largely a way to block claims that you might have thought were warranted. And you can even follow through my entire philosophy just with that negative thing, just blocking claims where very little, if anything, has been done in order to rule out errors. Claims where the probability that you would get as good a fit as you got, even though the claim is false, is high. Okay, so that is the block. I don't think that you would find that the answer, is continually no. What you should be doing is figuring out what, if anything, passes with a modicum of severity. Have you ruled out any way your claim can be false? And if you really can't say, and by ruled out, of course, I'm talking statistically ruled out, because none of this is going to be infallible. But if you really can't point to anything, then you don't have evidence. But I don't think that that's the typical situation by any means in science.
Maybe just to add some specific examples, so about sort of methods that have not even the smallest amount of severe testing has been applied to. I think you have some good examples, and I'll let you talk to those, the Texas sharpshooter, the trick deck questions.
Yeah.
And in your book, you also have a really great example on bioinformatics where that the Duke controversy, where essentially, I'll do that one, then you can talk through the other ones. But there's some bioinformatics researchers who essentially in cross-validation explicitly removed the data for which their models had poor prediction, and then claimed that people were failing to replicate their data because they weren't replicating it because they weren't taking out the data on which their model failed. So there's some interesting logic right there. But I think, yeah, I liked your examples as well. So maybe we could just go through those as just examples of how people sort of dance around not actually severely testing their work.
Well, the famous Texas sharpshooter, which is essentially my favorite, in allegedly trying to test their marksman ability, will draw a bullseye around wherever there's tightly clustered shots and claim that this is evidence of their ability. And of course, their ability, having it, would mean that they could shoot well with a pre-specified target, right? And so this is not evidence of that, because they can shoot randomly and find some clusters. And so that's a great example. The trick deck one, which is actually put forward by a likelihoodist, Richard Royal, points out that really the best fitting hypothesis, if you select randomly a card from a deck, would be that the entire deck contains all of this kind, let's say ace of spades. And he admits that using his own account of likelihood, where you're just looking at what hypothesis would make the data most probable, it is the hypothesis that it's a trick deck that contains nothing but cards of that sort. I mean, I think that's very problematic, but that's another example where you're going to find evidence for a claim and there was really no way you could have found that claim false. The optional stopping, trying again in the case of a two-sided normal distribution is a famous one, that if you go on long enough, the probability of being able to reject a null hypothesis of zero difference goes to 1, even though it is true. Similarly, a confidence interval would exclude the true value of, let's say, 0, if you're allowed to keep sampling. So these are cases, sort of classic cases that violate the minimal requirement for evidence.
Yeah, and if you don't mind, just to take a very quick detour on the issue of the likelihood principle, because I think that this is one of the areas where it is very helpful for the people who have thought deeply on these issues, where this is an example. The likelihood principle is something where when you first read it as an early career statistician, things like, oh yeah, that seems pretty reasonable at face value that you would want to be operating on these. And yet, as you can investigate further and further, the errors and the problems in it and the self-contradictions start to arise. And I think that one of the things that you have said well is that basically one of the values of adding philosophers to the mix and just having a more general examination of this is that the hand waving, the self-contradiction is more likely to be brought to the surface.
Okay, this likelihood principle is very appealing and follows from some accounts. It is telling us that the import of the evidence comes by way of likelihoods. Of course, to get a likelihood of a hypothesis, you already have to be within a model. And typically, this comes up when you're doing parametric inference within a model. Okay. And so if you're just going to say you have comparatively strong evidence for one hypothesis over the other, insofar as that one hypothesis is more likely in the technical sense than the other, then all this means is that that one hypothesis makes the data more probable than the other. But the thing is, you can data dredge and go optional stopping until you find some such alternative. So if you started with a null hypothesis, you could essentially always find an alternative that would be better supported than it. And therefore, on this principle, on this likelihood principle, you really would have greater support. So what's an alternative? Well, what Neyman and Pearson did is say the likelihood ratio is a good measure of fit, but now we need to know the probability that you would get such a strong measure of fit, even if the hypothesis, let's say the null hypothesis, is false. In other words, there's a second level there that says not all the information is in the ratio of the likelihood. You also need to know something about the method. And that requires that you take into account outcomes other than the one you observe, because you're trying to generalize about the method. Okay, this is a central difference between, let's say, Bayesian accounts and likelihood accounts, and typically called frequentist or error statistical accounts, which connect with the question of the role of probability in inference. So I really do think that more should be made of this in principle difference about the content of or information in the data, likelihood principle versus error probability principle.
Great. And just since you have the floor, where would you like to go from there? Because I think that there's a few places that we can branch off, and as the guest, I will give you the.
It's up to you.
Really? Okay. I mean, I was hoping to punt that decision to the expert. Why don't we talk a little bit more about how this severe testing can start help if not resolving these issues, at least better understanding the foundations of both these different camps. Would that be a good place to go?
That would be fine. Maybe I should say something about these terms. I use the term error statistic, and by that I mean accounts or methods where the role of probability is to ensure that misleading interpretations don't occur too often. So probability there arises to qualify the method. This is very different from assigning probability to a hypothesis. In a Bayesian view, by and large, it's completely reversed. Probability applies to the unknown, let's say, parameter value. What's the probability of heads on toss of a coin? Or does this drug prove to be beneficial? Is it beneficial for COVID? So they would assign probabilities to the hypothesis. The data, once it's available, would, if anything, be given probability 1, at least for a subjective Bayesian, because it's known. The error statistician instead is always interested in assigning probabilities to methods. What's the probability that this method would have produced evidence that is so impressively indicating a benefit, even though it's no benefit, or even though the benefit isn't as high as it appears to be? So that's the first thing. I think we often hear frequentist Bayesian, but frequentist is usually just understood as defining a notion of probability. And so I introduced this term, which really comes from error probability methods, okay, or error probability statistics. So for short, we call it error statistics. Now, error probabilities, things like confidence levels, probabilities of type 1 and type 2 errors, can be used to measure the capability of methods to unearth errors, and therefore they can be used to assess severity. This idea of severe tests, you could say, is kind of a meta notion. It's not directly a formal notion, but you can use these formal quantities that are available in order to ensure severity or in order to critically evaluate severity. This idea of severity actually comes from Popper, although he never adequately defined it. And so the idea is that a claim passes severely only if it is subjected to a test that would have found it flawed, and yet no flaws are found. So it passes a test that would have, with high probability, found it false if it is false.
And just to sort of bring a concrete example that everyone's familiar with, how would we, for example, incorporate the p-value into severe testing? Because this seems like this is, again, one of the reasons why we wouldn't want to throw out the p-value as a tool, because it is one of the ways that we would begin to start asking these questions about, is this claim severely tested enough to be acceptable?
Well, if it is a legitimate p-value, then you could use it. Certainly you can use it to block claims to have found a genuine effect. Suppose the p-value is not small, but is large. That means that the probability of an even more extreme result than you got, under the assumption that the effect that you're observing is just due to background variability alone, is fairly high. And so, as I had mentioned about our data dredger, you really couldn't take that as evidence for a genuine effect. And so what you would be saying, in effect, is that you're blocking the inference to a genuine effect because this is just the sort of thing you can readily bring about by chance alone. Okay, so it's very good at blocking when you're involved in the task of distinguishing genuine effects from chance. If it is a legitimate p-value, it is not going to be legitimate p-value if you have data dredged and multiple tested and so on. So then you can't use it at all, because you are saying that in fact it's very difficult to achieve an effect as large as I got by chance, when in fact it's very easy to achieve a result as large or larger even than you got by chance alone. So in other words, you're reporting an illicit p-value. Sometimes they're called nominal p-values, but they're invalid. However, if you have very often achieved small p-values associated with an effect, even a few times, you do have evidence of genuine incompatibility with the null explanation. So you may remember or not, but an example that stays in my mind is with hormone replacement therapy in the early 2000s, and they felt that it was really very beneficial for age-related diseases in menopausal, postmenopausal women. They didn't even want to do a randomized controlled trial because they thought it would be unethical. And when they did it, they found after many years that the probability of getting so many cases of heart disease, breast cancer, under the assumption of the general variability that you would expect in these was very small. It was the small p-values that actually led to a radical change in prescribing overnight. Okay. Now notice I said more than one. From the very beginning, R.A. Fisher, who was the founder of significance tests, insisted we're not interested in isolated significance tests. You have to be able to show that you can reliably bring about results that would rarely fail to be so significant by chance alone. And so that is often forgotten, at least for people who claim that a single small p-value is used to then go into print, and not only to infer that you have the genuine effect, but to infer some substantive theory about the cause of that effect. So that's just misuses of tests. So I do think that these methods, can serve up severe tests, but they're most important in showing when things haven't passed severely.
Yeah, I was actually going to say one of my follow-up questions that you just already answered was just the issue that does multiplicity essentially is multiplicity a good piece of evidence for the failure? For the failure to meet the severity method? Just really quickly, could we just as like some little check points, just because it's interesting to apply this to a variety of other issues that we have. So for example, when we have model checking and assumption checking or predictive performance checking, how would you just, should we just go through and just quickly discuss how those might fit into the framework? Just some sort of applied examples.
Well, it's very important anytime you're using a statistical model to be able to check the assumptions. And the assumptions might be independence, identically distributed, normally distributed. And actually statistical significance tests are the prime mode of performing such a check, because they don't require anything except the particular hypothesis that you're trying to probe. Okay, you don't even have to have an alternative except the denial of the claim that you're probing. It could be independence versus non-independence with respect to particular data. So I think when it comes to testing assumptions, all approaches that I know of go back to significance testing. I know that George Box, who is amazing about inference, says, well, we really have to be eclectic, because when it comes to testing assumptions, we really need to have statistical significance tests. We don't have an exhaustive set of all of the hypotheses we're going to want to consider, and we can't assume that we start out with all of the models that we want to consider. And so we have to appeal to those tests. So it's very strange when we have people who will use these tests for testing assumptions, but then will say there's something deeply wrong with the test.
I wouldn't mind talking about sort of the role with severe testing in as far as like scientific progress. I know that was sort of the question that I didn't phrase very well in the notes, but I thought it would be interesting.
I think that there's a general idea of scientific progress that comes out of the severe testing philosophy. And really, this is a philosophy of science. And therefore, what it's really doing is trying to give a perspective on all of the aspects of science and evidence and inference in order to, reflect on these issues and get through some of the controversies. I think that if we try to understand how we really do learn from data in order to figure out how to do it better, we can get this idea that what we really want to put together is what I call a repertoire of errors and mistakes, such that we can characterize, take for example, the anal potty. We can characterize sort of classic ways. This is very different from the typical list of fallacies that you see. So we characterize the classic ways that we have fallen into unreliable and insevere tests, but also ways in which we have managed to surmount the difficulties and the information gaps to severely probe. We amplify data, we check with independent means, and some of the techniques that data analysts have developed that you could try to do as well, try to get error probabilities, even if you are actually starting with the data, right? And that would be the way to do better in science. This count isn't a matter of just statistics. I talk about the levels from the raw data to modeling the data to statistical inference relating to the data to more substantive claims to high-level theories and models. And in fact, my book talks about particle physics and the deflection effect in science, and deliberately looks at the linkages from a high-level theory to specific data claims, because I really don't think it's such a big difference. People always sometimes would say to me when I was writing the book, oh, you're talking about Einstein's deflection effect. Well, that's sexy science, and we're doing, mere statistics. And I really think that you get the same kind of reasoning, because whenever you're trying to find effects, you're really looking at a more local statistical hypothesis. And once you do find an effect, like when high-level particle physics, they then want to find the properties of that particle. And then you're back to parameter estimation and confidence intervals. And so I tried to set out a way to delineate pieces of a large-scale inquiry and linking those to small-scale inferences, statistical inferences.
Well, Deborah, thanks so much for your time today. You brought up a large number of interesting questions. And for those interested, this chat is associated with a keynote lecture that Deborah has given, which will be a separate video. So for people who are wanting a systematic approach to this, check out Deborah's lecture video, and then this is one of the associated conversations with it. So Deborah, thanks so much for your time today. I appreciate it. There's a lot more left to learn, but thanks so much so far.
Thank you very much for your thoughtful discussions and all of the preparation.
Hey guys, it's Glenn. Thanks so much for listening to this most recent episode of the Philosophy of Data Science. I hope you enjoyed it. If you did, please consider leaving a like, a comment, and hitting that subscribe and bell button. We're a small channel and every bit helps. If you have a lab, a department, some students, or some colleagues who you think would enjoy this episode, please consider sending along. Again, every bit helps, and we really appreciate your word of mouth. Our next episode on the Philosophy of Data Science will be coming out 1 p.m. Eastern Time, Wednesday of next week, so we look forward to seeing you then. But if you can't wait to get more data science, machine learning, and statistical content, feel free to look around the rest of the channel. We have a large number of playlists, including things like machine learning for healthcare, ethics and AI, and things like that. So give a look around. There's plenty more content for you to enjoy. You can also check out our website to not only see past episodes, but what's coming up, and see who our sponsors are. Thank you to our sponsors for your support. Now, while the views discussed on the show typically range between extraordinary and mind-blowing, the stated views don't necessarily represent those of the host, our sponsors, my employer, your employer, the speaker's employer, or anyone else not saying those words. And as always, thank you so much for your time. I really appreciate it. See you next week.